about a topic that confuses a lot of people. We're talking about points of inflection, okay? So a point of inflection, I've got an example of two different ones underneath. This could be a point of inflection. Well, it certainly looks like one. This could also be. Now notice, this is a point of inflection, but it's not stationary. They do not have to be stationary. Stationary points can be points of inflection, but a point of inflection doesn't have to be stationary. A little bit confusing. So how exactly can we test a point of inflection? So it is not enough. It is not enough to just find this, okay? And I'm going to show you in a minute why this is not enough. What we're going to do instead is we're going to have this and we're going to look for a change in sign, okay? The reason for that is when we have a sort of a positive second derivative, it means that things are changing in a sort of positive way. It will create sort of a shape like this. When we have a negative, it means things are changing in a negative way. We will get shapes like this. And sort of if we put the two things together, where something changes its concavity, so it goes convex to concave, or the other way around, as shown by a change in sign, that's when we're going to have it. So let me show you. We're going to, first of all, kind of like find when it's equal to 0, if we don't already have information. But this is just so that we can inspect either side. It's not going to be enough on its own. If we have a change from positive to negative, or the other way around, okay, we'll have our point of inflection. If it stays positive or negative on both sides, there is no inflection point. So having a go with that then, we have x cubed in front of us. So x cubed, what we're going to do is we're going to differentiate first. We're going to differentiate again. And we're going to look at, when the second derivative is equal to 0, which would mean 0 equals 6x, x equals 0. Now this does not mean necessarily, okay, so I'm going to write that this is not enough. It's not sufficient. It does not mean necessarily there is a point of inflection. So what we're going to do is we're going to pick a value slightly to the left and slightly to the right. If I look at x equals minus 0.1 and x equals 0.1 with my second derivative, I'm going to look at what happens. So when I put minus 0.1 in there, maybe a little bit of notation, this is actually slightly easier if I write it like this. I get what? I get minus 0.6. So if it's minus 0.6, it's telling me that it's sort of changing in a negative way. It's telling me that it's concave at that point. If I do the same thing here with 0.1, I'll get a positive 0.6, which is convex. So there is a change in sign of second derivative at x equals 0. Hence, there is a point of inflection. And, visually, we can kind of see that as well, okay? It's when it's changing from one to the other. So it wasn't enough, and let me show you that it wasn't enough. So this is more of a problem if we have a more complicated function, but these are some nice examples. So second derivative again, 12x squared. If we solve that it's equal to 0, we get the same result, x equals 0. So we're going to look to the left and to the right again. We're going to look at minus 0.1 again, and we're going to look at 0.1 again. And we're going to see what happens. Now, if we put, that's a tenth, if we put it in there, it'll be 100th. So I will get a positive 0.12. I'll get 12 hundredths, so 0.12. Here I'll also get the same answer. So what I can see here is it's not changing from one to the other. In fact, it's changing in a positive way in both. It's actually convex and it's still convex. So if I had just solved equal to 0, it would have been wrong. So I really need to watch out for that. So there is no change in sign of second derivative. Okay, therefore, there's no point of inflection. Okay, so very common misconception, that one, but I hope those examples kind of show you why it's not necessarily enough.